This is how things like street lighting circuits work and how the central heating system works. It's how these things know, in inverted commas, to come on automatically when it gets dark or when it gets cold. So here's a simple series circuit. We've got a battery, a resistor, and a light-dependent resistor. Now, because it's a series circuit, we know the voltage push is shared out. Now, a light-dependent resistor is a resistor where the resistance depends on the surrounding light levels. And when the light levels go down, the resistance of the LDR, the light-dependent resistor, goes up. If the resistance of the light-dependent resistor goes up, the voltage share it gets goes up. So, what can we do with that? Well, if we know the voltage across the LDR is going to go up, then we can attach something called a transistor switch. Now, a transistor is like a little Manny with a barrier. So the transistor is a switch, it's like a little Manny with a barrier, which only opens up the barrier to let electricity go through the bulb when the voltage push across the LDR has reached a certain level. So when the voltage across the LDR reaches a certain level, because it's got dark, then the little Manny opens the barrier and electricity can flow down this loop, turning on the light in response to the darkness. So as the LDR voltage goes up, the transistor allows current to go through the bulb. These circuits look very, very complicated and very intimidating, but to explain them, just remember RVE. R stands for resistance. Talk about the resistance of the special resistor. What happens to the resistance of that special resistor? Essentially, the resistance goes up. RV. Talk about the voltage. Well, the voltage is going to turn up, going to increase, and this voltage increase is going to turn on the transistor. And E for effect, that transistor is going to allow current through something. RVE. Maybe you want to remember it as somebody's name beginning with R, vapes every day. So here's an example of a circuit. This is a circuit which turns on a bulb when it gets dark. So when it gets dark, RVE, the resistance of the LDR goes up. The voltage, the increase in voltage, turns on the transistor. The effect of this is that the transistor lets current through the bulb. Remember, the transistor is like a little Manny with a barrier, and normally that barrier is blocked. It blocks this loop, whereas when the barrier goes up, then current goes through. And here is a circuit where when it gets cold, that's a thermistor, the heater gets turned on. So when it's cold, the resistance of the thermistor goes up, the voltage share across the thermistor goes up, the transistor is turned on, which allows current through the heater. We're into the final topic. No way, this is energy. Done really well. Energy is not too difficult a way to finish, so hang in there, we're doing it, bring it. So energy, it allows physical actions to happen. There are a bunch of different forms of energy, and for some of these forms of energy there are formulas which allow us to calculate the amount of energy in this form of energy measured in joules. So kinetic energy, what we call movement energy in S1, is half times mass times velocity squared, or speed squared. Gravitational potential energy from something being high up is mass times gravity field strength times height. If you like a formula, there's the formula. Work energy, or physical energy, is force times distance. Work energy, it's got a bit of a daft name, but it comes from the idea that back in the day when people went to work, most people's jobs were quite physical jobs. So work energy, physical energy, is force times distance. Think about humping and dumping and moving stuff around. So if you've got something heavy, or you've got something and you're applying a force of 40 newtons to it, and you're doing that for 3 kilometers, what's the physical energy involved? What's the work energy involved? What's force times distance? Force is 40, distance is 3 kilometers, which is 3 times 10 to the power 3, and we get 120,000 joules. Just gave you an example for that one because that's the one which people find a bit tricky. Now, energy can be converted from one form to another. So if you've got a battery lighting a bulb, then the energy form which is in the battery is chemical. This energy is converted to electrical energy, which lights up the bulb, and the electrical energy which causes the bulb to light up, that energy is converted to heat energy and light energy. There can be calculations to do with energy conversions. So in this example, we've got a body of something on top of a slope, and the body rolls down the slope or falls down the slope. The body starts off with a bunch of gravitational potential energy. When it lets go and it goes down the slope, it's going to lose this gravitational potential energy, but this is converted into kinetic energy, movement energy at the bottom. The formula for gravitational potential energy is mgh, so this turns into kinetic energy, which is half mv squared. Stick the numbers in and you can calculate stuff like the speed at the bottom. So there you go, energy conversions allow you to calculate stuff. Another example of where you can use these energy conversions, if somebody throws a ball up and you want to find the height that a ball reaches, well, you can say, well, kinetic energy is going to be converted into gravitational potential energy, so half mv squared, which is the formula for kinetic energy, equals mgh, which is the formula for gravitational potential energy. And if you know the mass and if you know the speed with which the ball left the person's hand, then by doing this formula you can calculate the height which that thing is going to reach. Maybe it's a netball or something. Here's the formula for heat energy. EH equals cm triangle T. C is the specific heat capacity of the material. That is, how hard is it to heat up a material. Triangle T is the change in temperature. If you do want a formula triangle, here's the formula triangle. Some materials make it. Some materials take a lot of effort, take a lot of heat energy to raise their temperature, but once you've raised their temperature, they hang on to that heat for a long amount of time. Those materials which take a lot of heating to make them hot, but then hold on to that heat energy for large amounts of time, have a high specific heat capacity. So think about the insides of a McDonald's hot apple pie. It's molten, isn't it? It scalds you because the sugary water content in that apple pie filling has a really high specific heat capacity. The pastry around the outside has a much lower specific heat capacity. It doesn't hold on to the heat as well, even though all of that apple pie will have been heated to the same temperature. So yeah, things which heat up really quickly and cool down really quickly have a low specific heat capacity. Things which take a long time to heat up but then a long time to cool down have a high specific heat capacity, and the specific heat capacity of different substances is on the datasheet. Here's another formula for heat energy, and people get confused a bit, but this formula, EH equals CL, it's all about the extra energy to melt a solid or the extra energy to vaporize a liquid version of this thing. So the heat energy required, the extra heat energy required to melt or evaporate something is the mass of that thing times the latent heat value. Now the latent heat value is on the data sheet. Again, it's different for different materials, and if you're talking about vaporizing something, then you need to choose the latent heat of vaporization. If you're talking about melting something, then you need to find the latent heat of fusing. I don't know why they call it fusing. It's stupid. They should have called it the latent heat of melting, but they don't. They call it the latent heat of fusing. So when you are melting something, it takes extra energy, so that takes heat energy out of something. So similarly, when you're vaporizing something, that takes heat energy out of something because it needs extra heat energy. It takes heat energy out of the surrounding. So this is why sweating works. Lovely example. So when water, which is what sweat mostly is, turns into water vapor, then that state change needs extra heat energy. Where does that come from? It comes from your body. So that's why sweating is so useful for taking heat energy out of your body. If you put ice cubes in your gin and tonic, when these ice cubes melt, this melting needs extra energy. That extra heat energy comes from the drink, and this is why ice cubes keep your gin and tonic nice and cold. So here's some graphs. if you're doing lots of sport, your temperature goes up and up and up, but here's where you start sweating. Your body temperature doesn't keep rising because the sweat is taking all this heat energy out of you. And that's good, because if your body temperature keeps getting hotter and hotter and hotter, then you start feeling dreadful. So because of the sweat evaporating, taking this extra heat energy away, then your body temperature actually stays fairly stable when you play sport and doesn't keep on rising dangerously. You can see on a graph where you've got something solid and it's being heated, when it starts to do the state change, the temperature doesn't keep going up because of the extra heat energy required. Then when the solid's turned into a liquid, well, the liquid, if you keep heating it, then the liquid temperature goes up and up and up. Now here we've got state change, so even though you're keeping heating the thing, the temperature isn't going up because all this extra energy is going into the state change. So the horizontal parts are the places where state change is happening, and it works the opposite way around. The reason why getting a scald, let's say you put something in the microwave and then you pull it out and you peel back the cling film, if you put cling film on top, and you get a horrible scald. The reason why the steam scald is so bad is that the extra energy is now coming out because the steam is hitting your hand and it's condensing. So the extra energy associated with that state change is now coming out on your hand because it's turned from a water vapor to a liquid, and that extra heat energy is giving you a burn, a scald. We sometimes want to find the specific heat capacity of a block. So here's an experiment to find the specific heat capacity of a block. Remember this formula, EH equals cm triangle T. So if we want C, then we need heat energy, we need mass, and we need the change in temperature. So we have a block, we have a heater inside the block, and we have an energy meter, and we have a thermometer. So we turn on the heater and raise its temperature a bit. The thermometer gives us the temperature rise, the energy meter gives us the heat energy involved. We've measured the mass of the block before, and from that we can solve to find the specific heat capacity. Sometimes the SQA just like to make life tricky, and rather than electricity meter, we have some sort of variable voltage power supply, and we have an ammeter in the circuit. So we've got V, we've got I. From I and V we can work out power, and then we can say P equals E over T, and we can solve to find E, because the question will tell us how long the heating has been happening for, and the question will also tell us the power of the heater. Right, then the question quite often says, why isn't the C value found from this experiment the perfect value? And the answer is, well, not all the heat energy from the heater goes into the block. Well, where else could it go? Well, it also goes into heating the air around it. So if you want a better value for the specific heat capacity, a better value for the specific heat capacity, if you wrap this whole thing in insulation, then less of that heat energy is going to be lost to the air, so a greater proportion of that heat energy goes into the block to raise its temperature, and so you get a better value for C. But remember, this is just heating something up and letting it cool down. If you've got a state change, if you've got melting and evaporating, then that takes extra heat energy, and the extra heat energy, that's all to do with latencies. I think this might have been in the wrong order. I've got to be honest, I think, yes. Sorry. There we go, that would make more sense, wouldn't it? Here we go. So this is the order it was meant to be. Introducing specific heat capacity. Then we were going to go on to the specific heat capacity experiment. Then we were going to talk about the extra heat energy involved in the state change. And then I would have shown you this. Oh well, I hope you followed it. We've got one formula for just increasing and decreasing temperature of something, and that formula is EH equals cm triangle T, and they've got another formula for if there's a state change involved. Okay, I'm not going to redo this. I think you can follow it. This video's been long enough already. We're almost getting there. We're almost there. Right, pressure. Pressure is force over area. Force in newtons, area in meters squared, and therefore pressure is in newtons per meter square. But a newton per meter square is also known as a Pascal. So if you've got some ice on Kepty Pond, why does somebody walking out normally on Kepty Pond fall through it? Whereas if somebody lies on Kepty Pond and crawls out, then they don't fall through it. But please don't do that. Well, it's because the area of somebody's